Good morning, everyone. My name is Wenxue, and today I'm very happy to present our recent work, PolicyCache, Intra-flow Learning in Congestion Control. First, let's look at existing congestion control paradigms. The heuristic-based schemes, they use rule-based or rule-based rate control or congestion window control. The good thing is that they are simple and lightweight. However, they brittle under unseen conditions. And the learning-based schemes, they deploy a model learned from training networks. They are responsive but suffer from poor cross-environment generalization and high overhead. And the third one, the exploration-based schemes rely on online trial and error to probe the best rate. They are adaptive but have slow responsiveness. So why do existing paradigms fall short? The first way, the most learning-based and heuristic-based schemes, they follow inter-flow learning, which means they apply a policy learned from one set of flows to other flows. An offline learned policy is generally responsive. However, it may fail in new networks due to variation in link characteristics. The second aspect, the exploration-based schemes, they rely on online probing, making minimal assumptions about network conditions. Each probe requires normally several RTTs to generate the next action. So they have great adaptability and can converge to a large, to a good working point under various network conditions. However, they suffer from low responsiveness, especially in some high RTT or highly dynamic network conditions. Therefore, we pose the following question in our project. How can we leverage both the proactive responsiveness of learning-based methods and the adaptability of exploration-based methods? So we propose intra-flow learning. Intra-flow learning is a paradigm in which both the learning and the execution of the learned policy are confined to a single flow and its corresponding path. So under this paradigm, a new flow starts with no prior policy. It collects state action pairs during transmission. It updates the model online, and it uses the learned policy for later rate decisions. And the question is, why does intra-flow learning help? First, there's no pre-trained policy assumption, so the system learns and applies the policy within the same flow, avoiding mismatch across distinct different paths and network conditions. Second, it learns statistically to reduce noise sensitivity. It learns based on the flow's trajectory instead of reacting to one-shot noisy feedback. And the last one, it improves control responsiveness. Once flow-specific patterns are learned, the policy can make fast control decisions without waiting for multi-RTT exploration. However, there's a key challenge. Intra-flow learning requires fast online adaptation from limited samples within a single flow. So existing learning-based congestion control algorithms rely on parametric models such as neural networks, which converge very slowly before becoming useful. So in contrast, non-parametric models such as decision trees can immediately utilize new data and adapt within only a few update steps. Therefore, we need a non-parametric model, the tree model for the intra-flow learning. So now let me introduce the overall design of our proposal, PolicyCache. PolicyCache has two parts. The control path has the control path takes network signals and chooses between two modes: the backup exploration mode and the tree model execution mode. Backup exploration is slow but robust, while the tree execution is fast once the policy is learned. So the action router decides the network. The action router decides which path to use, which mode to use, and outputs the descending rate. The learning path collects network signals and rate decisions, converts them into training samples, and finally updates the tree model online. So the workflow is simple. A flow starts with no policy, explores first, collects data, updates the tree, and then switches from the exploration mode to model execution mode once the tree becomes available. This is why we call it PolicyCache. It learns policies online and caches them in the model for faster retrieval. PolicyCache uses a Hofding adaptive tree, or HAT for short. HAT is suitable because it learns incrementally from streaming samples. When a new sample arrives, it's routed to a leaf, and the tree updates its statistics. Once enough evidence is collected, the tree uses the Hofding bound to decide whether to split. This allows fast online learning without expensive neural network training. HAT also supports concept drift, so when the network condition change, outdated parts of the tree can be replaced. So the tree model gives PolicyCache fast adaptation, low overhead, and online learning capability. PolicyCache uses backup exploration when the model is not reliable. In backup exploration, the sender probes with both increasing and decreasing probing pairs. Then it computes utilities from throughput, RTT, RTT trend, and losses, and chooses the direction with higher utility. This is robust but slow because feedback takes several RTTs. To keep collecting labels during model execution, PolicyCache also uses a mechanism called micro-exploration. It slightly modifies the model updates and uses the feedback only for data collection. So backup exploration provides safe control, while micro-exploration keeps the model watched and updated during fast execution. PolicyCache collects data for two purposes. First, for updating the tree online tree model, and second, for updating the model performance score. Because the network feedback is delayed, so PolicyCache aligns each explored good action with the earlier state that caused it. So this gives reliable training samples. The same samples are also used to monitor the model. PolicyCache compares the model update from the explored good action. If they agree, the score increases. If they disagree, the score decreases. The action router then uses this score to decide whether to trust the tree model or just fall back to the backup exploration mode. We implement a fully functional PolicyCache prototype on Linux. It consists of two main components. The kernel handles the signal collection, backup exploration, and action enforcement. The user space process handles HAT training and the inference process, model switching, scoring, and sample alignment. We use the showing tools for low latency kernel space communication, for lightweight online HAT implementation, and for evaluation. First, we first demonstrate that PolicyCache maintains consistent high utilization and low latency across diverse, emulated, and real-world networks. We evaluated a PolicyCache with varying bandwidth, varying latency, varying random loss, and buffer size. In all this experiment, PolicyCache maintains consistent high performance. We also test PolicyCache in inter-continental and intercontinental environment, and PolicyCache still maintains very good performance. Next one, PolicyCache converge much faster than exploration-based congestion control mechanism due to its model execution mode. It also maintains stable throughput and delayed jitters thanks to its exploration mode. In contrast, the learning-based congestion control mechanism such as Astria can be misled by some noisy RTT signals. We also evaluate fairness and friendliness. For fairness, PolicyCache achieves the highest fairness ranking across multi-flow settings. Flows with different RTTs share almost equally bandwidth. For friendliness, PolicyCache achieves more balanced coexistence with cubic and BBR. We also provide a convergence proof in the paper. Check it if you are interested. PolicyCache has, here we show that PolicyCache has lower overhead in terms of CPU utilization than most of baselines. It's much lower than the learning-based, than the neural network-based congestion control mechanism, and achieves comparable overhead with this heuristic, very standard algorithm. So its efficiency comes from lightweight online tree model learning. This slide shows that how dynamic switching works. The rule is simple. High score means tree inference, and the low score means backup exploration. During stable period, the flow is almost close to the optimal rate. So at this point, increasing or decreasing the rate can have similar utility. So the best direction becomes stay here. Therefore, the score may stay below the threshold, so the exploration mode works safely. After a bandwidth change, new samples reveal a clear directional bias. So the model and the score are updated, and the score rises above the threshold. Then PolicyCache switches to tree execution mode and reacts quickly. So PolicyCache uses only the learned model when it's reliable. To conclude, we introduced a new congestion control paradigm, Intra-flow learning. We designed PolicyCache with an online tree model, backup exploration, and a dynamic switching module. PolicyCache achieves high responsiveness, adaptability, and low overhead across diverse networks. Thank you for listening. Please feel free to contact us for more details.